And I'm going to show you a new technology that we developed for reinforced ceramic behaving material, and concrete is one of them. Here we go. So up to now, the systems, the methodology for reinforcing concrete has been embedded rebars, pre-stressing, and post-tensioning. I think we all know quite well those kind of systems. The material used has been steel, mostly, and in recent times, also FRP came up as a reinforcing material. Basically, the main problem with the embedded rebars is that concrete start to fail with a strain in tension that is about 100, 120 microstrain, but the steel typically get a yield at about 2000 microstrain. So means that when you are embedding a rebar, you are not very effective reinforcing the concrete, or at least stopping the cracking, because the rebars need to be placed away from the area because corrosions and so on. Basically, you are also reducing the effect of the reinforcing. The pre-stressing stress, basically the sharing between the pre-stressing and the concrete happen by shear most of the time. And for the same reason, they must be placed away from where the maximum tensile are, because otherwise we have risk of splitting for various reasons. The post-tensioning is the more expensive way, but you still have some corrosion risk in case of a poor grouting. The problem with the material used is about the steel. You have a short life cycle due to the corrosion. Corrosion in steel is actually the main cause of failure of any kind of reinforced concrete product. You have it is a material with a very high environmental footprint. Is about 2 kilograms of CO2 for each kilogram of steel. The cost, as we know, and rapidly lose strength in a fire when the temperature starts to exceed a given amount, maybe a little more of 400 Fahrenheit. But the FRP bar on the other side, they have a low Young modulus for at least for materials that are usable in the construction industry. Obviously, you can have, FRP rebar that have even 400 gigapascal, but obviously you go to PBO or to carbon fiber. That is not something that is usable for cost reason. They have normally long-term creep, and that happens basically because if we look at how the fiber is actually done, the composite is actually done, you have a bunch of strands that are the fibers that are embedded in a matrix. And what happened is that when you are casting that kind of rebar, or are using that kind of rebar or that kind of composite into a casting, like a concrete, basically most of the time, like in a pre-stressing application, the shear is around is getting to the external of to the skin, let's say, of the bar, and the central area where you have fibers is transmitted to that fibers only by the tangential modulus of the resin, which is extremely low. That means that basically that is the reason why you get shear, you get a creep, long-term creep, and because increasing the section of a composite, you don't get very much increasing of total strength. Basically, you drop the specific strength. Then they have a low fire resistance because obviously resin matrix, they burn at relatively low temperature. And when the matrix is gone, basically you have only the skin that is holding the load. The cost, that because for the kind of rebar that you can use, I mean, that they have affordable cost, like glass or basalt most of the time, because they have a relatively low Young modulus, you are forced to increase significantly the section and come up having a big amount of impact on the cost. And then we have also some environmental footprint. You have to consider that in any kind of composite, the fiber itself is not that bad from an environmental standpoint. The matrix, it can be extremely heavy. Just few numbers. On an epoxy, making an epoxy, you get roughly 6 kilograms of CO2 for each kilogram of epoxy. The FRP reinforcing is actually getting more and more important, mostly because the new environmental impact things are pushing cement producer to having concrete that are more friendly from an environmental standpoint. And all those concrete, they basically have lower pH. The game to obtain a better and more environmental friendly concrete is basically to convert a little bit some of our calcium hydroxide and having with CO2 and having calcium carbonate, which obviously it's a little stronger, but it's setting faster, but is lowering the pH, which means that it's not providing passivation to the steel anymore. They can use with the lower concrete cover because obviously they don't have corrosion problems, and they have much greater service life. So here, what we came up with, trying to put together all the best of the various things, we came up with this quite weird idea, probably. So the idea is to use the fiber as a roving to be wrapped around the concrete product or other kind of material with ceramic behavior, impregnated with a resin while it is still wet. So basically doing in this way, we obtain, so basically we make a wrap on an area, on various area. It can be round, it can be square, it can be any kind of shape. So obviously if it's a, let's say, if it's a square, you have a biaxial compression. If it's a round, you have a hoop stress, induced hoop stress. And basically doing that, what we obtain is that we have a much lower creep. And that happened because we are not using anymore the resin to share the load between the fibers, but it's actually the friction. Since each singular probing is tensioned, is pre-tensioned, and then locked together, basically you don't have any more, you don't care basically about the elastic modulus of the resin, because basically everything is transmitted by friction and everything is already preloaded. Because it's preloaded and is wrapped around, basically we have a very high fiber resin ratio that you can't get with a pultrusion. There is no way to get there. Basically because you are wrapping around each other, so you are creating a pressure and the excess of resin is coming out, which means that you can get fiber resin ratio that they are very, very similar to the use of a prepreg. It's a kind of fiber that is used in aerospace mostly. You get a very high fire resistance with this system because basically, even if the resin burns completely, since the wrapping are overlapping, the friction that you have between the various wrapping is not loosening anything. Everything stays together. Even if the resin burns completely, you don't have any loss of tensioning. And if you are using fibers like the basalt, up to 650 Celsius, you basically do not have any decrating. It's lower cost because obviously you are tensioning the fiber, so you don't have any more an oversizing of it. You have a larger spectrum of application because basically you are going to have the reinforcement that is outside on the skin of the product. So basically you can start to do things that now are not possible. Like you can glue together parts and you can generate out of a small standardized component, very big element, because you can shear, I mean, you can transmit the forces to the fiber that is wrapped around, and so is not, you are not just relying on the poor shear strength of the concrete. You are taking advantage of the lower Young modulus, basically because you are stretching it. So adding a lower modulus come up in adding less loss of pre-stressing or post-compression. We name that process post-compressing, because if you have a little bit of shrinkage, obviously, and you have a high modulus, you get quite a bit high loss. But if you have, let's say, if you are using basalt, you are looking about 70, 75 gigapascal modulus, which versus steel, that is 200, 210. It's quite a bit less. So you have almost 1/3 of loss of pre-stressing. And all those processes, they can be highly automated. It's another advantage. Yeah, basically, yeah, yeah, no, if I'm able to, I show you a little video on how that kind of combination between concrete and this kind of post-compression system works on a pipe. That technology was actually developed for Duke pipes, and then we expanded a little bit another way, if I'm understanding how that thing works. Okay, sorry. You can get this effect because two reasons. Basically, it's compressed to about 10 MPa, that material, and you have an effect of confinement and as well of post compression. So basically, you come up with something that has a behavior that is. You are putting together two materials that has a, let's say, a brittle behavior, but you come up with something that is having a completely different behavior, mostly because also the geometry, the wall is very thin and so on. Okay. As I was saying, with this technology, you can do also things that have not been possible before. Here we see like a floor system made of product that they are wrapped. On the bottom one, you can see here that basically, because you have the wrapping around, you can actually create holes with a little piece of metal that are spreading the load, and you can cross the wrapping around the product, and you can actually start to joint parts, creating larger structure, but smaller parts, and you can transmit significant moment with this system because basically it's a full moment joint. And for smaller things, you can do actually by gluing, like we have done walls and that kind of things. You can even, I mean, for smaller things that where you don't need to be disassembled, you can actually glue everything together. Here is the attempt that we did on a tie, on a concrete tie. As you see, the behavior is relatively different from what happened on a steel reinforced tie. You can see the first section where you have a stiffness that is more or less the same as a pre-stressed tie. Then you have a crack. Then the stiffness becomes 1/3, and you have a failure with an enormous deflection. That is what we are going to make, basically. It's a tie that has a, let's say, a shape that is is an halfway between a composite and the concrete, because you have obviously the wrapping, the post-compressing wrapping, and then, but the core is actually concrete. So that is what we are going to make, and we will test probably at MXV. With that design, basically you can switch to dry cast production method of the concrete. So basically mean immediate stripping, because you are applying the compression later when the material is cured, so you don't need to have anything in the bed. Because the dry cast production method is an immediate stripping process, you normally have a water cement ratio that they are varying between 0.25 and 0.32, 0.33. So because the very low water cement ratio, you can normally get for the same strength level, you can get normally between 20 and 25% less cement percentage. You have a lot higher overload capacity. If we are thinking to pre-stress concrete ties, normally you pull the wires at about 85% of yield. This is a composite. So basically, even if you are using basalt, that is something that has a relatively a behavior very relatively similar to carbon. The maximum place where you can go is 50%, because it's brittle and because that is what it is. So means that if for a few cycles you get, let's say, to stress level that are even 2 times, nothing happened. If that happened on a steel, we all know that steel get relaxed and soon it will fail. You can use obviously environmental friendly concrete, like I was saying, and you can get a better dampening because you can tune everything to a lower level of pre-stressing. First of all, because you have the fiber that are in the area where you have the maximum tensions. So you don't even need that amount of stressing, but if you reduce the dampening, there is an interesting study done from a Turkish railway that is showing the dampening about noise at various levels of pre-stressing. And basically, when you get to a relatively low pre-stressing level, the dampening happens a lot, is increasing a lot. You have a very low conductivity. Obviously, you don't have steel. It's corrosion free. And even if you get a crack in the concrete, basically there is nothing that corrodes. Thank you for your attention. Below the pad, we are going to put a polymeric concrete, which is epoxy mixed with silica sand. So we may grind the rail.
I'm referring to your banding. So what happens if it abrades and it abrades through? Do you lose all your compression?
Well, before we were speaking about GFRC, reinforced ties, is exactly the same things. So you don't have big problems in the meaning that is exactly like a composite, and you have thicknesses in the order of 5 millimeter of wrapping. But if you are using basalt, actually, and here there is a sample, you can even see it. To get through, you need to use the diamond wheel. It's not a soft material. It's
And glad to see high technologies are booming all over the world. We have presenters from Germany, Italy, Brazil, and the United States. And let's give a round of applause for all the presenters today. Thank you.